Hello everybody, this is Cameron Snow with Danomics.com. So today I'm going to be bringing you another Danomics Basics video, and in this case we're going to be looking at how we can calculate total organic carbon, or TOC, as you've probably heard it referred to. Now, when do we want to calculate TOC? We want to calculate it whenever we're working with organic shales. So if you're working in formations like the Wolfcamp, the Barnett, or the Woodford, which you'll probably run into in places like the Midland and Delaware basins, or if you're working on things like the Niobrara or the Mowry formations, which you would come across in places like the Powder River Basin or the DJ Basin, this is a property that you're going to want to calculate. So first of all, TOC is a property that we can measure in core. So you should have some of those measurements available. You can measure it not only from whole core, but you can also measure it from cuttings. So it's a very easy property to measure. It's also very cheap to measure, and labs can generally turn this around quite quickly for you. So really you should have calibration points available to you there. Now, with that said, let's go through the theory of how we do some of these calculations. So I'm going to start off with the modified Passey method. So you'll notice here in this middle column, we have the RO curve and a deep resistivity. And what we're going to want to do is we're going to want to make these curves align with one another. Now, you may say, Cam, how do I know what the resistivity of bound water is? And the answer is you don't know. And the reason why is because we can't measure that property. So what we do is we find an inorganic shell layer and we adjust the RWB until we see it collapse with the resistivity curve. And in that case, we'll have no excess resistivity because these are inorganic shells, and we're looking for those organic shells with that excess resistivity. So keep your eye on this track here. And what we want to do is we want to adjust RWB to make these curves roughly overlie one another. Now we see we're pretty close there. I can tweak that just a little bit more. And now we see we have really tight alignment between these curves. And we see that it's doing an excellent job of highlighting the organic shells here in the Niobrara formation. So that's giving us a very high TOC result shown here in the black curve. And that's what we would expect for this formation. Now the other parameter here is maturity. This is also a property that you can measure. You should note that Passey originally used what he called level of maturity in his correlation. However, I'm framing it in all of these examples as equivalent vitrinite reflectance because I think that's a number that most of you are more familiar with. Okay, so now that we've got that set, let's take a look at some of Passey's other methods. So let's take a look at his overlay method. So you may have heard about delta log R or D log R. Well, that's the overlay method for the sonic log. But we're also going to be looking at this for both neutron and density. The property, the concept is the same in all of these. And these are overlay methods, meaning that what you need to do is you're going to need to set the baseline values in a inorganic shell so that the curves overlie one another, and then you will essentially take that information and turn that into a quantitative result. So to get started, let's look at a cross plot because we want to set our resistivity of clay first. And so here we can see we have our clay resistivity. And at our highest clay values, we've got around 3.5 to 4 ohms of resistivity. So, we can come in here and we can set that value at 4 ohms. Now, where do we need to set it for our sonic, density, and neutron values? Well, this is where the overlay comes into place. So let's set this at a very low value that's a bit nonsensical for learning purposes. When we do that, we see that we have a lot of separation here. So we'd be calling a lot of TOC in this interval that we know as organic shell. So let's increase that value a little bit. Okay, now we can see that we've almost collapsed that to where they're overlaying. let's do that one more time. And now we have these curves overlying one another, and we have our result. Okay, let's repeat this exercise for density. So let's set our density at a relatively high value. Oh, we went the wrong way with it there. Let's set it at a relatively low value in this case. All right, let's let's back that up to where we get rid of what appear to be organic material here. And okay, we're starting to eliminate it through here. Maybe we need to take off a little bit more. And now we have the organics that are predominantly only showing up in our Niobrara interval once again. And then we can repeat this method with the neutron curve. Okay, we get these to overlay on the inorganic shales. And what we see is that we have pretty good agreement between all these methods. We may want to, to try and be internally consistent, we may want to dial down the results a little bit from our density method to really get that to line up with what we're also observing from the neutron and sonic values. Okay, a few other methods that we have available to us. We've got things like the Schmoker method. We have some other density-based methods like Vernik, and we also have another sonic-based method, which is Faust. So let's take a look at Vernik's method. So once again, this is a method where we only have to set one parameter, and that's the rho B of clay. Now notice that in this case, I have set my rho, it's a separate rho B clay parameter than what we're setting from the Passey overlay method, but these numbers are often quite similar. And what we're looking to do here is, let's try to lower the shale or lower the TOC result in our inorganic shales and keep it elevated in our organic shell interval. I've actually found that both Schmoker and Vernik work really well in the Midland and Delaware basins. They don't seem to work quite as well in formations like the Niobrara, and I wonder if that's not due to its more marly nature. And let's end up with the Faust method. Now, Faust is one I really like because there's really nothing to set in Faust. It's almost a parameterless method. We do have a fudge factor, which is the formation multiplier in this method. But I often find that Faust gives us a very robust answer, and it's one that you can use as a nice calibration for a starting point on some of your other methods. Now, unfortunately, it requires having a sonic curve, which I know a lot of the times you won't have access to, which brings me to which method is really the one that you're wanting to use. Well, it depends on what data you have available. With the some of the Passey methods, especially like the Passey neutron method, all you need is a neutron curve and your resistivity curve, and you're good to go with that one. Both those curves have been around for a long time. With the modified Passey method and the Passey density method, what you're going to need there is a density curve as well as the resistivity curve. So, also very common in most logging suites. And it's really not till you get to the delta log R methods or the Faust methods where you start to need that sonic curve to make that. Now, once you have calculated this, it's imperative to say that we want to calibrate this result. So you would want to, as I said earlier, obtain the TOC data so you could calibrate your methods, calibrate your parameters, and make sure that you're not being overly or underly aggressive on your interpretation. So that's one key. The other thing that you need to keep in mind is that we're calculating this TOC in a weight percent. And if you're going to feed this into something like mineral inversion, you're going to want to convert this to a kerogen. I find that the old Schlumberger method for converting TOC and weight percent to kerogen and volume percent is quite robust, and that is the one that I typically go with myself. And with that, I'm going to leave you to explore this a little bit on your own. If you have any questions, you can feel free to let me know. And if you'd like to do a trial of Danomics and see if you can calculate this yourself, feel free to reach out to me at sales@danomics.com. Thanks.